Brilliant. Yeah, thank you for the introduction, and thank you for inviting me here to talk about what we do as a company. So I think, yeah, I'll cover more about what Strangeworks does more towards the end of the talk. I'll talk about what it is that we're trying to do and how we fit into the wider quantum industry. But first and mostly today, what I wanted to do is give you a little bit of an introduction into variational quantum algorithms for gate-based quantum computers. So the goal here, my intended goal here is not to make everyone an expert in these techniques by the end of the talk. It's just to sketch out the general ideas and give you all of, um, excuse me, give you all a flavor for how these things work and what sort of problems they can be applied to. Okay, so one class of variational algorithm is called the quantum approximate optimization algorithm, or QAOA for short. So of course, this is not the only variational algorithm in this field, but it's a good starting point for getting into these things, I think. So mostly these methods have been applied to solve this class of mathematical problem. Okay, I know this looks quite abstract, but it's very important to understand because almost any with an asterisk, any logistical or optimization problem can be written or described in this form. So it's very general, and that's the reason it's received a lot of study, and it's the reason that lots of people are interested in solving this type of problem. I'll come back to more in a few minutes on some of the specific problems that can be mapped into this form. So these things, they're called QUBO problems, another acronym here. So this B in the acronym stands for binary, and this means that these variables, these xn's, these are binary variables. And so these variables can only take two possible values, in this case 0 or 1. And the other important point is Q, this Q term, this Q word in the acronym, this stands for quadratic, meaning that in this expression, only terms up to quadratic order are represented. So there are only terms with products of two of these variables, or single terms, or terms with a single variable. And so there are no higher order terms or higher order product terms. Okay, so, let me take you through a simple example here, and I find it's best, or it's useful to visualize these QUBOs as graphs. And so this is what I try to do here. So we have 4-node graph shown here, and this means that we're representing a QUBO with 4 variables. So there's 4 xn's. So each of these nodes represent one of our variables, one of our xn's. And if we have a vertex between the two nodes, this means that these A coefficients, these are just real numbers. They are non-zero if we have a vertex between the nodes. But if, for example, if we don't have a vertex, between these two nodes, for example, that means that these A coefficients are equal to 0. So there's no coupling between these two variables, but there are couplings between these variables. Okay, and so we're then looking for this for a solution to this graph. That the solution means what is the values of these nodes, what are the values of the variables, what sort of which nodes are 0 and which nodes are 1. So we're looking for this solution that maximizes the number of vertices cut. So this is the max cut problem. This is a simple toy problem, but it's nice to illustrate these things. So for example, here's a solution. And so this turns out that this is the most optimal solution for this particular graph. So we have this node is pink, this node is blue. So because these are in two of the different classes, instead of 0 and 1, I've got blue and pink. Because these two are in the different classes, we've then cut to this vertex, and that's what it means to cut the vertex for the solution. And so notice then that actually with this solution, we've cut all of the vertices here. So this is why this is the most optimal solution, because it's the solution that maximizes the number of cuts to this problem. In addition, we have this solution, so this is different to this first solution, but notice that it also cuts all of the vertices, so it has the same value for the cost function, and so is also an optimal solution. And so I just wanted to highlight here that with these types of problems, it is possible to have 2 or even more degenerate solutions that are all the optimal solution. Okay, and then take this solution here. This is a solution that it has a correct or a distribution of zeros and ones that satisfy the requirements, but in this case, we only cut two of the vertices. So although we have cut two of the vertices, this gives rise to a larger cost function, and so is not the optimal solution that we will be looking for. And so, of course, this is a particularly simple cuboid graph problem, and we can guess the solution pretty easily just by looking at it. But however, if we had a more complicated problem, with more nodes or more vertices between the nodes, then it is currently an open question for how to solve for the optimal solution in all cases. And what's I think is also important to note that in most cases, we will settle for a solution that is only slightly better than the currently obtained or utilized one. And so what I mean here is that if this is actually a real optimization problem for an industry setting that has been mapped to this cubo form, while of course they are looking for the most optimal solution, this is the most desirable solution. If we are able to find a solution that is even a fraction of a percent better than the currently utilized one in the industry setting, then we could potentially save a substantial amount of money and resources. So in formulating this problem, formulating a solution to this problem, it's not necessarily the best case that we're looking for. It's just we're just looking for a solution that can beat the current best solution found from an alternative algorithm. So, it's been proposed here that perhaps we can use quantum computers to help us here, giving us a new set of systems to improve upon alternative classical optimization methods. Okay, so how do we do this on a quantum computer? Well, for each variable in our problem, we need a single qubit. So we've got four variables, four xn's in our toy problem. Then we need four qubits in order to describe the solution. We then apply this quantum circuit to the qubits, and for the moment, it doesn't really matter what this quantum circuit is. Different ansatz circuits here can potentially work better for different problems, and it is currently a extremely important open question in the field on how to accurately determine which ansatz is best suited for which problem. But we'll not consider this at the moment, and maybe we can discuss this later. Okay, so we apply our circuit to the qubits, and then we measure the resulting qubits. And I'm sure all of you know this. When we measure a quantum circuit, we destroy the nice quantum properties, we destroy superposition, we destroy entanglement, and what we get out is basically a classical result. We get out this single classical bit string for the values that our qubits take. So, for example, we measure the first qubit in state 1, the second qubit in state 0, and so on. Then if we do this, repeat this experiment and do it again we get out a classical result, but it can be a different bit string, 0011 in this case, for example. We measure a third time, we get a different solution, fourth time, fifth time, and so on. And so then what we do is we repeat this hundreds of times or even thousands of times, and we create this probability distribution. And so, what this shows is the sort of number of times that this particular bit string has been found throughout our thousands of runs. So, this bit string's been found this number of times, this bit string's this number of times, and so on. And so note that this, while this doesn't give us the actual quantum state of the system before the measurement, it does give us an indication of the relative weights or amplitudes that these states had in the underlying quantum superposition. Okay, great. So now we have a probability distribution. We've applied the quantum circuit hundreds of thousands of times, and we're happy that we have enough statistics to accurately estimate this quantum state. Next, what we do is that we take these measurement results and we classically compute the cost function for our particular problem, cubo or graph. So what we do is for each of these bit strings, each of these measured states, we substitute the bit string into this cost function expression. So going from this line to this line, I've just replaced our xn variables with what I'm calling qn, which are just the values of the bit string that we've measured for that particular state. So for example, for this state, for this bit string, all of the q's are equal to 0. For this one, all of the q's are equal to 0 except the last one, and so on. So now we have a sequence of cost functions. Oh, and so substituting these bit strings into this expression is a classically simple calculation, which scales linearly with the number of variables. So it's doable on a classical computer. So we take then these cost functions and we put them into this final expression where now we take the cost of that particular solution and we weight this by the amount of times that we've measured that particular solution. So we've got the weight of that solution the cost of that solution weighted by the probability that that solution will occur. And oh, sorry, and that gives us the total cost function. Okay, so that's great. We've got the total cost of this quantum state for this particular graph, but what do we do with that? So we put this cost into a classical optimizer, something like steepest descent gradient minimization, or perhaps something more complicated if you want to, try to refine or improve on these things. So, we have this quantum circuit that we've applied, and this is we've parameterized this quantum circuit with these classical variables that I've denoted by theta here. And so this is a set of classical variables, and these could describe the rotation angles in some of the quantum gates, for example. And so we've then applied this quantum circuit to our qubits. We've prepared the quantum state, we've measured the quantum state enough times that we built up the statistics, and we've computed the cost function. And then we then can take the classical optimization algorithm, we put the cost function into the classical optimization algorithm. This can then change the value for these theta coefficients slightly, create a new quantum ansatz circuits, which then we can apply again. We can prepare that quantum state, measure that quantum state, and compute the new cost function. And then the classical optimizer can then decide, well, how do we change these theta values such that we can lower this cost function? And what this process is trying to do is it's trying to find the optimal value for these theta coefficients such that we find the lowest possible cost function, which gives us the solution to the QUBO. So there's this quantum classical feedback loop, which is why these variational algorithms are usually referred to as quantum classical hybrid algorithms. And so, okay, so that's all I really wanted to get into at the moment. Now, of course, there will be time for questions at the end if someone wants to ask about one a particular aspect of these things. Also, for more information, see these references here, and you can even search into Google QAOA Qiskit, and the Qiskit textbook is a really nice worked example with a downloadable Jupyter notebook for QAOA, so you can really sort of get to grips and see what's going on here. Okay, so I said before that basically any problem can be mapped into a QUBO form with, a huge list of theoretical toy problems that basically cover anything that you want to do in optimization. And so, see this link for a really nice extensive list of the types of problems that can be solved or formulated like this. With this list seems to be growing by the day. It's really really useful. In addition, though, there's a growing number of real-world industry use cases for these QUBO problems. We have things like supermarket chains optimizing distribution networks. We have the optimization of bustle shut routes through a busy city in real time. And we have things like optimizing the order in which vehicles in a factory are sent through a paint shop, optimizing things like the number of color switches, etc. Now, note that all these things come from D-Wave. In particular, see this link here. This has got a really huge list of industry use cases that, it's getting very exciting. And, of course, D-Wave is not a quantum computer in the conventional sense. It doesn't have qubits. It doesn't have logic gates. It's a quantum annealer. And so, all of these use cases are coming from the annealers at the moment because, at the moment they are more sophisticated and, actually they are beginning to have the capability of solving large enough variable problems to begin to actually become useful to the real world. Now, in the future, the hope is that gate models, or more than the hope, it's expected that gate models that use QAOA should be able to reach similar performances and potentially go even further with a wider range of applications. Okay, great. So just in the last few minutes, I thought it would be nice to just tell you about Strangeworks and what it is that we do here. So, Strangeworks was founded about 5 years ago. First of all, we were a community platform focused on education and dev tools with, the development of quantumcomputing.com. Today we are moving more towards an enterprise-ready platform, so that something that is more useful to enterprises and industry setting. People actually doing real use cases. The way that we've tried to design these things, the approach that we've taken, is we want to make it easy for the user to select whatever resources they would like, be that classical resources, GPUs, high-performance CPUs, or quantum resources, QPUs, gate-based devices, or quantum annealers, as well as being able to select individual applications for their needs. And we wanted to design this in a fairly modular way so that we can take these things and so the user can take these things and apply them into their existing workflows in whatever environment they've decided to use, their whatever environment they're currently using in their industry workflows. And on top of that, we've tried to build on top of this a way to manage the sort of expense of all these things across different systems, different quantum systems. And we've incorporated the ability to manage people in your team or manage the architectures of all of these resources on one platform. On top of that, what we offer is that you don't have to do any of these things alone. We have one of the largest networks of partners across hardware, software, consulting, education, and government. And we believe that this then enables us to provide the best product catalog and platform that we can build and deliver. And so, what, in addition to taking these things that have already been done or are already offered in the platform that you can use, we also have the opportunity to work with the customer to build customized services for a user's needs. So, and then the way that we're able to access these things, we can do this, the user can do this through two different environments. First of all, we have this sort of like command center. This is this web-based user interface that allows you to enable people into your team, add systems into your team, allocate different resources into these members, and manage billing all under one platform. Additionally, we have this downloadable software development kit that one can install, and you can work with and you can integrate this into whatever existing development environment that the team is currently operating with. And these things communicate with one another. If we were to submit a job to a quantum hardware through the development kit, you'll be able to see this job or your list of all of your jobs on the platform. You can click on the job and you can see a nice graphical display of the results for that job. And so finally, just on the final slide, all of these services or derivations of services will be made available to our customers via our public future compute marketplace. And so, you'll be able to use anything that you've developed internally within your own organization. You can keep this private and just have it internally, or you have the ability to share this to this wider marketplace, putting your created services, making these accessible to wider organizations so that other people can make use of your nice new algorithm that I guess you have then the potential then to find new use cases and just grow this community together. So one final note, we are sponsoring one of the prizes here at QHack, and the prize includes allowing you to work with our applications team, probably including me, to help you put a custom service onto this platform. So you get our hands-on expertise and the opportunity to make your method, algorithm, whatever, accessible to all of the people in our community. So with that, thank you very much for listening.
Thank you so much, Stuart. I like seeing your marketplace. That's something that I hadn't seen before. You have a lot of stuff that is novel and different. So I encourage everybody to try out and keep exploring Strangeworks. We also have questions. So we're going to go first with a question from QHack. How do VQAs compare to quantum annealing? Is one better than the other for particular problems?
Say that as how do VQEs compare to quantum annealing?
Variation quantum algorithms, I think.
Oh, okay, yeah. So the sort of physical principle underlying these things are different. Okay, it's both quantum, but annealers work on this quantum adiabatic principle, whereas VQEs really have this sort of sort of this conventional optimization approach, where you have this you're trying to find the best parameters to find the desired solution. So I guess the formulation is a little bit different. It's very complicated. We can spend all evening going into the nitty-gritty details of what the underlying physics is with each method, which I won't do. How does the performance compare? I think that's an open question at the moment because the gate-based devices, at least the free hardware is only accessible through IBM, up to, what is it, 7 qubits. And I think that in the hackathon, you may get access to 16 qubit devices. So you may be able to test this out. Even if you did a classical simulation of these things, at most you can get up to 30 qubits. And D-Wave annealers are operating with 1,000 variables. So it's really difficult to compare the two because they're operating on really vastly different scales. I think we're going to have to wait a couple of years for the gate-based hardware to become sophisticated enough to really compete with the types of problems that D-Wave can solve. And then it will be very interesting to actually do a brute force comparison. Of course, then the other thing I should say that D-Wave can only solve QUBOs, or annealers can only solve QUBOs, whereas gate-based quantum computers, in principle, are capable of universal computation. So once the gate-based get to that stage, maybe they might not outperform solving QUBOs, but there'll be something else that they'll outperform in. Hopefully that answered your question.
I think it did. For me, the answer was very clear, so thank you for that answer. We have also a question from Cultiviert. QAOA provides good performance for problems such as max cut and max sat. Do you happen to know an example problem which is not well suited for QAOA and why?
Yeah, so for example, if you're trying to find, so in quantum chemistry, if you're trying to find the ground states of a particular molecule, you have this quantum Hamiltonian. QAOA can't solve as many Hamiltonians as VQE. So VQE is variational quantum eigensolver. So it's very, very similar conceptually, but is different. So QAOA is really best suited for QUBO problems, which have a classical solution. Alternative variational algorithms like VQE are better suited for more complicated quantum algorithms, more complicated quantum problems that have a quantum solution, like finding the eigenstates or the eigenenergy of a molecule.
Yeah.
Okay.
I think that was a good answer. You have to really think about what is your problem, and then if it looks kind of like a chemistry problem, then most likely you will need something like VQA instead of QAOA. And if you have something that looks a little bit more like an optimization problem, maybe QAOA is the way to go.
Exactly. If it's a QUBO, you would apply QAOA or an annealer.
Mm-hmm. Okay, thank you so much. Thank you so much for your answers and for your presentation, Stuart. It was great having you. Hopefully, everybody can keep asking questions on the Discord. And
Absolutely.
yeah, see you later.